My greeting to Dr. Mohammad Arif Sazali. We are from Group 3, consists of Zulaikha, Sharul, myself Naveen, and Maisarah. Now we're going to do our presentation on experimentary, which is application of first and second law of thermodynamics. Now we go to the first part, which is abstract. The experiment was conducted to understand the concept of first and second law of thermodynamics. A small beaker containing boiled water was placed into a big container. The container was filled with cold water and thermometer was used to measure the temperature of the water of the hot and cold water. Temperature of both water was recorded in each minute until thermo equilibrium is reached, where the temperature of both water supposed to be same. The small beaker and big container was weighed in different conditions as required for the further calculation. Approximately 19 to 20 minutes were taken for the water to reach equilibrium, which was 35 to 36 degrees Celsius. The graph of water temperature versus both hot and cold water was plotted.
Assalamualaikum and hello Dr. Arif. So my name is Sharul Reeza. So today I will be presenting the introduction, the theory and also objective for our experiment. So in thermodynamics, there are three laws of thermodynamics, which is the first law, second law and third law. But in this experiment, we are going to focus more on the first and the second law. So the first law of thermodynamics, also known as law of conservation of energy, states that energy can neither be created nor destroyed. So energy can only be transferred or changed from one form to another. So for example, turning on a light would seem to produce energy. However, it is electrical energy that is converted from electrical to light energy or heat energy. So this law states that there are two types of processes that can cause a shift in internal systems internal energy, which is heat and also work. So since both heat and work can be measured and quantified, any change in systems energy must be accompanied by corresponding change in the energy of the environment outside the system. So to put it in another way, energy can neither be created or destroyed. So next, the second law of thermodynamics states that the state of entropy of the entire universe as an isolated system will always increase over time. The second law also states that the change in an entropy in the universe can never be negative. So to put it in simple word, heat cannot flow itself from colder body to hotter body. So the second law of thermodynamics used to determine the quality of energy. So it also to be exclude the possibility of constructing 100% efficiency of heat engine because it will violate Kelvin Planck and Clausius statement of second law. For the objective of the experiment, we want to apply first and second law of thermodynamics in various processes. For the theory, the change in total energy system can be calculated by total energy entering the system minus total energy leaving the system, or E in minus E out. Since energy of the system is equal to delta U plus delta of kinetic energy plus the change in potential energy. So since the system is not moving and there's no elevation in this experiment, so we can cancel both kinetic energy and potential energy and we leave with E in minus E out is equal to delta U. So the delta U system is equal to delta U hot water plus delta U cold water. So from that, we can use the heat equation, where heat equation is equal to M times Cp times T2 minus T1 of hot water plus M times Cp times T2 minus T1 of cold water, where M is mass, Cp is heat capacity, T is temperature. So for the Clausius statement, the Clausius statement states that it is impossible to construct a device which operates on a cycle and produce no other effect than the transfer of heat from cooler body to a hotter body. So heat always has a tendency to move from high temperature to lower temperature. And if we want to do that, we need to supply from some form of energy. So in conclusion, the Clausius statement say that Temperature can be only transferred from hot reservoir to cold reservoir.
Hello, I am Zulaikha. So now we are going to discuss about the apparatus and also methodology used in this experiment. Okay, so this is the apparatus that has been used. We have kettle, small beaker, stopwatch, weighing balance, big container, and also thermometer. Methodology. So firstly, the water was boiled in the kettle. So then while we're waiting for the water to be boiled, we need to measure an empty small beaker, which then we put it on the weighing balance and we weigh it. Then after the water had been boiled, we need to pour that water into the small beaker and then it was weighed again. Okay. Next, the small beaker that after we weighed it, the small beaker uh, which contained a hot water was moved carefully into a big container. And like here, we have a diagram here how it will be. We we put the hot water into the container. Okay. Then after that, the cold water was poured into the big container without entering the small beaker. It means that we only pour the cold water between the container and also the small beaker. So the cold water was filled until it reached the same level with the hot water inside the beaker. Okay, so then make sure that the cold water was not um, pour or mix into the hot water, which I said before. We need to pour it between the container and also the small beaker inside the container. Okay. Then the cold water poured just now was weighed after this. Okay, then we need to set up our thermometer into both of the cold water and also hot water. Okay, so the temperature in both water were recorded in each minute, in every minute, using the stopwatch until it reached the same temperature, which was the thermo equilibrium. Then, lastly, the data was then recorded into this table. Thank you.
Assalamualaikum, and my name is Maisarah, and I will be continuing the presentation for the result and the discussion. As you can see here in the slide, the data that we used is there are three data that we use. The first one is the heat capacity of the water, which is constant 4.187 kilojoule over kg Kelvin, and the mass of hot water used and the mass of cold water used. And as you can see here, look carefully, the amount of cold water and the amount of hot water being used was a little bit different. With the cold water being used is quite bigger, more than the mass of hot water being used. This is important because later on the discussion part, I will tell you why. And on the right side, you can see a table with the first column is the time and the temperature of hot water and the temperature of cold water. And for the time, we use 1 minute time interval to take the temperature reading. And the the initial temperature for hot water is the 85 degrees Celsius, and the final temperature is 36 degrees Celsius. As for the cold water, the initial temperature is 28 degrees Celsius and the final temperature is 35 degrees Celsius. Okay, moving on to the first result, which is the graph. This is the graph that we plotted using the data previously, which is the temperature for both hot and cold water with time. As we can see here, solid blue line is the temperature for hot water and the temperature for cold water is this solid orange line. The hot water releases energy in the form of heat. When we do calculation later on, we can see the result will yield negative value, and the negative value indicates that the energy is out of the system. That is why the temperature of hot water here, the blue line, is decreasing, or we can say having the negative gradient. As for the temperature of cold water, we can see the trend having the positive gradient. And the calculation also, we can see later on the energy change you will see that it will yield positive value, and this positive value indicates that the energy is being absorbed or is going inside of the system. And the dotted or the dash line, the blue dash line here indicates the linear for the temperature for the cold water, and the dash here you cannot really see it, but there is a dash line, the dash orange line here, which is the linear for cold water. And this is the uh, equation that we obtain using the curve fitting method for both dash line. Okay, this is the calculation part that I mentioned earlier. The energy change for hot water and for cold water. The first thing first is we need to find the temperature difference, which the formula is very simple, which is the temperature final minus temperature initial. Because the data that we use or we collect, we use the degree Celsius. That's why we need to convert it into Kelvin. So 36 plus 273.15 minus 85 plus 273.15, and we get negative 49 Kelvin. And this is the formula to calculate the energy change. E equal to m Cp, the heat capacity of water, and this is the temperature difference here that we calculated already. And the mass for hot water is 0.203 kilogram, and the Cp is constant for 0.187 times the negative 49 is we get negative 41.6481 kilojoule. This is what I mentioned earlier, that we get the negative value, which indicates that energy out of the system. That's why in the graph we get negative gradient. The calculation for cold water is just the same, just the input for the temperature is different, which we after calculated we will get 7 Kelvin, and the mass we use for cold water is 0.730 kilogram, and the final result we get the positive value, which indicates that the energy is going inside of the system. And this energy this energy in is from the energy being released by the hot water. And moving on to the discussion part, there are several observations that we can make during the experiment was conducted that can prove the first and the second law of thermodynamics. And the very first obvious observation that we can make is, as soon as the cold water was being poured inside the container that contained the smaller beaker with hot water, both temperature for hot and cold water immediately starts to change. As for the cold water, it started to increase, and the cold water started to increase, and the hot water started to decrease until both the temperature reach constant value, which is 36 degrees Celsius and 35 degrees Celsius respectively. And the reason why we get this constant value at the end is because both water has already reached thermal equilibrium. And in this thermal equilibrium state, there is no heat transfer between this both water. Or we can say that the temperature change in this moment is zero. That's why we obtain this constant reading. And another observation that we can make is that the rate of heat transfer is proportional to the rate of temperature change, which means that the higher the heat transfer, the bigger the temperature change in both water, and vice versa. As the smaller the heat transfer, the smaller the temperature change in both hot and cold water. And furthermore, this has something to do with the mass of water that we use. As I mentioned at the very beginning, that the temperature change for hot water is bigger compared to the cold water due to the large volume of cold water that we use compared to the hot water. And the first law of thermodynamics is concerned about the conservation of energy, which means the energy cannot be created or cannot be destroyed. And the first law of thermodynamics stated that the conservation of energy in a system where the net energy must be zero. And in this case, for our experiment, we can see that the the value of energy being released by the hot water is not the same as the amount of energy that is being absorbed by the cold water. Here, this is the value of energy that is being released by the hot water, 41.64. And this is the value or the amount of energy being absorbed by the cold water, which is 21.39, which is almost half of the energy being released. So where is the other half of the energy being released? So the energy is, we say, lost to the surrounding. Because this experiment was conducted in an open system. But that is not the only reason why this phenomenon happened. This can also occur due to some error made throughout the experiment. Later on, I will discuss on what are some probability errors that is being made in the experiment. And again, from the result obtained, the change energy for hot water, we get a negative value due to the inclining in the temperature, which means the energy is being released from the hot water. And the energy is being released is being absorbed by the cold water, and it can be proven with the positive energy change for cold water, which means from the calculation earlier. And therefore, we know that heat will flow spontaneously from the higher temperature to a lower temperature. In this case, the higher temperature is the hot water and the low temperature is the cold water, with no external input, which is work being done to the system. And this means that this process is obeyed the second law of thermodynamics, because the second law of thermodynamics stated that a process will occur in a certain direction, not just in any direction. For example, the waterfall will fall from a higher position or higher level to a lower level. There is no such thing as water going up from here, this level to this level. It's possible, but there will be some work. We need to do something so to make it possible. And that is what the second law of thermodynamics is all about. And we move on to some error that may occur in the experiment, which contribute to the experimental result deviate from the theory. And the first thing is, I think the most common thing is the parallax error, which is the eye level of the observer is not aligned with the segregation mark of the apparatus. And another factor is that the apparatus is not positioned properly, which makes it hard for the observer to take the reading. And the second one is the thermometer may accidentally touch the beaker, which may alter the value obtained and the accuracy. This is because, as we can see here, there is no much room for the thermometer being placed. The mushroom between the smaller beaker and the big container. So the probability that the thermometer touch the side and the bottom of the container is very high. So it will contribute to the result deviate from the theoretical. And the third is the no stirring process was done, again due to the limited space between the beaker, and result in the unevenly distributed heat transfer throughout the system. And the last one being the container was not insulated, causing the heat loss to the surrounding. So we need to do something, or we need to take some precaution to avoid this error and to improve the result and the accuracy that we get. And for the first problem is obviously when taking the reading, make sure that our eyes level are perpendicular to the scale so that we can get the accurate result. And also what helps is taking the average value. at least 3 times. And then make sure that the all apparatus used is positioned and held properly. And the second one, ensure that the thermometer does not touch the bottom and the side of the container, or simply use a bigger container to give larger space or to provide larger space. And the third one is use a bigger container, provide space also for the stirring process to be done so that the heat transfer will be transferred equally throughout the system. And the last but not least is the insulator. We need to use insulator to insulate the container to minimize the heat loss to the surrounding. And I think that is all for my part. And I will pass the next presentation to my group member. Thank you.
In conclusion, the water took 19 to 20 minutes to reach equilibrium, which was 35 to 36 degrees Celsius. The water temperature of hot water was decreased and the temperature of cold water was increased until equilibrium is reached. The plotted graph proves that the water reached equilibrium at the 19th to 20th minute. The rate of heat transfer is proportional with the rate of temperature change. The experiment proves that the first law of thermodynamics is valid where no heat transfer when the hot and cold water reach thermal equilibrium. For the hot water, the temperature change was negative 49 Kelvin and the energy change was negative 41.6481 kilojoules. The negative value in the energy defines that the temperature was decreased and the energy being released. For the cold water, the temperature change was 7 Kelvin and the energy change is positive 21.3956 kilojoules. The positive value in the energy change defines that the temperature was increased and energy being accepted. The transfer of heat from the hot water to the cold water proves that the second law of thermodynamics is valid. That's all from us. Thank you.